7:15. Happy Friday, everybody. We are going to get started with a kind of mix of review of last time, something I didn't get to finish at the end of last time's lecture, and then we're going to see how far we get with new material today. Okay. So I am going to start by drawing something out here. Remember we talked about a voltage divider last time, so hopefully you believe me, without even really having to do any math, that if, for example, I have a voltage divider with two equal value resistors, so 10 volts in, two 10 kilo ohm resistors, in the ideal case, I'm going to get 5 volts out. Okay? And the equation, you should have written down from last time, V out equals R2 over R1 plus R2 times V in. So if R1 and R2 are equal, that's just 1/2 V in. You get half the voltage out. That's the ideal case. Last time we kind of briefly talked about what happens when you hook a multimeter up and how a real multimeter does have some non-infinite internal resistance to it. So if I have my two 10 kilo ohm resistors and I hook up my multimeter, which is kind of like putting another very large resistor, we're going to call it 1 mega ohm, in parallel there, what is my actual V out going to be? Okay, I'm going to run this as a poll everywhere word cloud where I just want you to type in the number with no units up to 3 decimal places. Okay, so if it was 5, you would type 5.000, and hopefully that prevents the word cloud from being a mess of different numbers of decimal places. No LeBron this time, just numeric numbers. I can go see what your individual answers were, so if you type in LeBron, you don't get the participation credit. Please type in the actual number. I'm not going to show it real time. I'm going to give you a couple minutes to work on this and show it at the end. Again, this is ultimately just going to be graded for participation, assuming you enter a real answer. So don't worry about rounding if we're off by 1,000th of a volt or whatever, but I kind of want to see my plan for now for Poll Everywhere. Is to continue using it as participation credit because it helps me. Basically, I don't want you to panic and be afraid about being wrong in lecture because it helps me gauge if there's a misconception, and if I explain something poorly and a lot of people are getting it wrong, that'll help me correct it. So in the past, the iClicker software lets you do like a full credit for any answer, or sorry, full credit for correct answer, half credit for any answer, just kind of for showing up, and then no credit for no answer. Apparently, Poll Everywhere doesn't let you do that. So I'm just going to continue doing participation credit. So if you aren't sure, try to do the calculation, enter whatever your answer is, but don't worry if you don't have the exact numerical answer that I have. So I will give you a couple minutes to work on this as I look at, we only have about 9 or 10 results in. We're usually up over 100 people, so I'll probably wait until we're up over 100 before I kind of start counting down. So take your time. And this is just kind of mental exercise, preparing you for both, or for homework 2, and just kind of simple resistor stuff that you're going to need to be comfortable with throughout the rest of the semester. And again, this isn't just analyzing imaginary resistors, this is representing what happens when you connect the multimeter to a circuit. And the fact that the act of connecting the multimeter actually impacts. If you are just joining us, there's a Poll Everywhere up for this problem. Please enter V out, just the number, no spaces, no units, up to 3 decimal places. And I guess while people are working on that, a couple quick announcements. One, some of you are getting, again, same thing with homework 1, getting an early start on homework 2, which is great. But that means you might actually be getting a little ahead of me in lecture. So, and I saw there was a question on ed discussion about current sources, which we kind of ran out of time last time. There's also going to be a problem on homework 2 about something called node analysis. which I'm hoping to at least start today, depending on how far we get. If not, we will start it Monday and hopefully finish it Monday so you have it in time to get homework 2 done. If you are like really trying to stay ahead of things and want to do homework 2 over the weekend, there is a video about node analysis in that intro circuit theory playlist linked on Canvas. So if you want to watch that in advance and work on homework 2 ahead of time, you can. But again, we are going to get to that in lecture today and Monday. Okay. I am going to do another lap. We are at around almost 70 responses, and it looks like Friday attendance is a little lighter, just kind of looking out at the crowd than what we saw earlier in the week. So we'll see if we get up over 100. And feel free to talk to people next to you if you're stuck and not sure how to do this. Okay, we are at about 115 responses, and it looks like it's leveled off, so I am going to switch over 120, 121 to showing the results. And unfortunately, the word cloud thing did not work like I wanted it to here. It looks like it splits the words up based on the period, so we but you can see the 4 and then the 975. So 4.975 is the answer I got, so at least that still kind of worked. And then somebody, again, I know units, and the answer should be a voltage, not ohms. So whoever entered 96 kilo ohms, I think you might have misinterpreted the question. And then a lot of the other decimals in there, I'm assuming or hoping were 4 point something close to 5 volts. So again, if you didn't get that right, don't worry about it. I will kind of work through the correct derivation here. So I'm going to close that, deactivate, okay, and here, switch back to the document camera. Okay, great. So there's probably more than one way to go about doing this to arrive at the final answer, but I'm going to show you how I did it by combining resistors. So remember the equations for resistors in series and parallel. I'm not going to write them down again, but I can merge this circuit with 3 resistors into a circuit with just 2 resistors, where this one is the equivalent of these 2 in parallel, right? So I still have my 10 volts in, I still have 10 kilo ohms there. This one is going to be R EQ equals 1 over 10 kilo ohms plus 1 over 10 mega ohms, the inverse of that whole thing. So again, that comes from the equation for equivalent resistance in parallel. If you do that, again, depending on how careful you are about rounding and significant digits and all that, which to be honest I am not, 9,900.99-ish ohms for that equivalent resistor. Okay, we now know we have 2 resistors in series. So the current through them has to be the same, right? And I can combine them into a single equivalent resistor for the whole circuit. Oops, sorry, that should just be one big resistor there. Adding them in series, that's just 10,000 plus this 9,900. 19,900. Guys, remember, if I can hear you talking up here, you're way too loud. Okay, I don't want to have to treat this like a middle school classroom. I've got kids at home I have to deal with. I don't want to have to treat you guys like kids. So please, if you're still talking, like, if you want to wrap up a quick conversation about the previous problem, fine, but like, please don't just continue talking while I'm trying to talk. Yes?
In series, is the resistor 1 mega ohm or 10 mega ohm?
So this one here on the right, so the original individual resistor is 1 mega ohm. Oh, you're right, I see what you mean. That should just be a 1 there. Thank you for catching that. I'm absolutely not immune to mistakes, so if you ever do, don't just like let me keep talking for 10 minutes after I wrote something down wrong. Thank you for catching that. Okay, so we then combine in series, add those two, roughly 19,900 something ohms, apply Ohm's law there, V equals IR, just to our single resistor, so 10 volts equals I times 19,900.99 ohms. We solve that for I, which is some really small number, 0.0000502 something amps. Thinking about units, and usually, I think I mentioned last time, we're going to be dealing with milliamps in this class, not amps, so you could rewrite that as 0.5 something milliamps. If you don't want to write out all the zeros, just keep track of your units, make sure you're not off by a factor of 1,000 or something in your final answer. So I know, again, the current through this resistor. If I kind of look back at the original circuit, that current I has to flow through this resistor R1, and then it splits through the other two. Right, so you could say, okay, well, I want to figure out what the current through each of these individual resistors is, and then if I know that, I could figure the voltage drop over them and figure out V out here. You actually don't have to bother doing that, because if you know the current through this resistor, from Ohm's law, you know the voltage drop over that resistor, and you can just subtract it from 10 volts to find the voltage here. So you can kind of go either way. And in that case, I'm going to say V out is actually 10 volts minus the drop over, I didn't label these initially, but if I call that R1, if I call VR1 means the voltage drop over resistor R1, which using Ohm's law is 10 volts minus I times R1. Those are all known values, right? I now know I because I just calculated it. R1 was a given, so that's 10 volts minus, not bothering to write out all the decimals, 0.0005 something amps times 10 kiloohms, and that's where you get the final answer of V out equals 4.975 volts. Great, so at the end of the day, what does that actually mean? Hooking the multimeter up changed the ideal voltage by a couple hundredths of a volt. Okay? As far as we're concerned in this class, again, if you are checking the voltage of a battery and you want to see if the battery is fresh, right, like a 1.48 volt AA battery is probably, compared to a 1.5 volt AA battery, not really a huge difference. It's not like it's dropping it by a whole half a volt or something and would give you this false reading that you actually have a dead battery. Okay, so yeah, as far as we're concerned in this class, that change of, a couple hundred or tenths of a volt or something doesn't really matter. But clearly for more precise applications, right, if you're just measuring something that's in the tenths or hundredths or millivolt range to begin with, then that can make a difference. And then that does, again, there's different settings on the multimeter that let you kind of measure different ranges. So remember that when you hook your multimeter up to measure something, the act of hooking up the multimeter causes the voltage to sag slightly. Okay, questions on that? Yes?
Are you permitted to use the voltage divider equations just using R2, the equivalence, like R equivalent of having each?
Yep. So the question was, can you, rather than kind of doing what I did here and looking at the current through R1, can you use the voltage divider equation here with REQ? Also yes. So when I said that there's kind of more than one path to ultimately arrive at that answer, what we are going to get to with node analysis, again, hopefully today, maybe Monday, is as we'll see in kind of the next example, as you start adding more resistors, so in the simple case, the two resistors, you have the easy voltage divider equation. As the resistor network gets more complicated, slogging through and doing it manually like this kind of becomes more and more cumbersome. So there is a way again, called node analysis, to set up a system of linear equations that you can then just solve using linear algebra all at once. So rather than kind of, okay, I know this variable, now I can plug it into this equation to solve this variable and doing it all one step at a time, you just get a 2x2 or 3x3 or 4x4 matrix or whatever it is, and then you just solve it all in MATLAB instead of doing it like this. So that is where we are headed, again, hopefully by the end of today's lecture. Any other questions on this? Okay. You remember what I wanted to do next. Okay. I want to circle back to current sources now, because this is on homework 2. Again, we kind of ran out of time to talk about them last time. So again, some of this might be a little redundant with what I wrote down last time, but I don't remember exactly where I stopped. Current source, we represent as a circle with an arrow in it like that. It gets positive and negative terminals, just like a voltage source. But with a current source, the current is known, voltage is unknown. Okay, so this is maybe a little less intuitive. Can I spell? No, I'm not. Okay. Voltage is unknown. And so this is probably less intuitive than a voltage source. This means if I hook one of these things up to a resistor, just like that, right? Resistor R, the current I is determined by the source, but Ohm's law still applies to the resistor, right? So I can calculate the voltage that the source will provide based on Ohm's law. Just like if you hook a voltage source up to a resistor, you can calculate the current the voltage source will provide based on Ohm's law. Same thing here, it's just the current is determined, and again, we drew this graph last time, the IV diagram, where we say that the current source can provide a constant current and ideally could provide infinite voltage, but in reality, again, just like a battery cannot provide infinite current, a current source can't provide infinite voltage. So the problem with this is that as R goes to infinity, for a constant I, then that would mean that the voltage also goes to infinity, right? Which clearly isn't physically realistic. So just like with the batteries and the voltage source, we modeled a practical or real voltage source as having a resistor in series, which prevented that current from going to infinity. For a practical current source, we model it with a source resistor in parallel. So call this, source resistance R source. Out here is your load resistance RL, where again, this is a mathematical model. Everything inside this box represents my current source. And now again, even if RL goes to infinity, then I still have some resistance here that's going to limit the voltage that the source will actually provide. Okay, and if we look at this node, we are going to talk more about nodes in a minute. So if I have the total current from the source coming from the ideal part of the source there, I have current going out to the load, and then I have current kind of going through that internal source resistance. So I can apply Kirchhoff's current law there. IS equals IL plus IRS. Flip that around, so the actual current delivered to the load is IS minus the current kind of dissipated through that internal resistance. Use Ohm's law to write that, and when IS is the constant, again, that's the current provided by the source. Use Ohm's law to rewrite this current as Vs over Rs. So if you think about this as IS is the ideal current provided by the source, IL is what's actually delivered to the load. Your load is a motor or whatever, you want as much current as possible to actually go to the load, which means you want, ideally you want this term to be 0, which means you want Rs to be very large. So that's the opposite of what we had for a voltage source. Since that internal resistance is in series, we want we want the resistance source to be very small for a voltage source. For a current source, again, think of it like you want as much current as possible to go through that resistor over there, so you want this resistance to be really, really big so it doesn't siphon off too much current. And again, this is a mathematical model of current source. There's a question on homework 2 that talks about solar cells. So solar cells actually behave more like a current source as opposed to a voltage source. But in practice, we're not doing anything solar powered in this class. Most of what you're physically going to be dealing with is either batteries or the benchtop voltage sources. But again, this is something, put this on the list of like things you're not going to have to deal with that often, but you should know about going forward. Okay. Question, and again, there's a video about current sources on Canvas if you're sitting down to do homework too and kind of want more of a reminder about that. Questions on the current source thing? Okay. We are going to do another kind of, we're not going to do this one as a poll everywhere, kind of a symbolic example of the resistor network analysis situation as a motivation for node analysis, which again, hopefully we're going to get to today. So, resistor network analysis. Using the equivalent resistance method, which is what we did before. What happens if we kind of keep adding more resistors? So if I have a circuit with 4 resistors instead of 3, and we're just going to do this symbolically because this is kind of how I recommend working through this type of problem. R3, R4. So resistor R1 in series with R2 and R3, which are in parallel, which are then in series with R4 in a single battery. And thinking about what this physically represents, maybe R1 and R4 are long wires, which are then connected to some 2 resistive loads in parallel, right? Again, like a heating element, okay, toaster, space heater, those little like hot plate stirry things in a chemistry lab, anything that's a purely resistive load as opposed to a motor, which we'll talk about later. Okay, be careful about sign convention. Remember, you can go through and define kind of positive and negative for each resistor here. If you define it the opposite way and then wind up getting a negative number when you solve for the current through one of them, that just means the current is flowing opposite of the direction you defined. Pardon me for a second. So let's say that, hint, hint on a homework or an exam, somebody gave you a problem like this and, okay, said solve for everything through resistor 2. I want to know the current, voltage, I want to know I2, the voltage drop over resistor 2, and the power dissipated by resistor 2. Right? How do I go about doing that? And you can kind of follow the same process I did for the voltage divider example when it was just 3 resistors, but what I recommend is keeping it all symbolic until you get to the very end, and then you just have one equation where you plug in all the resistances. So again, I apologize in advance. I'm going to stand here and slog through this. I realize that you were all probably excited about the robot on day 1, and now you're sitting there like, this is boring as hell. I promise it gets better, okay? This is probably my least favorite part to teach because it's just kind of slogging through a bunch of algebra. Like, the topics should get more exciting as we go on. But again, in terms of learning objectives of the course, like being able to analyze a resistor network and understand current, voltage, and power dissipation by resistors is something you need to understand coming out of it. Okay? I literally met someone at a conference once who just was like, the Mechis I know barely know Ohm's law, right? So you want to be literate in this as a professional. So not the most exciting thing in the world. I'm doing my best. Bear with me. Okay. So following the same kind of steps I did previously, I'm going to start out by combining resistors. So I can combine this, and I'm not going to bother redrawing the sign convention thingies each time, but I can combine those 2 resistors in parallel. I'm going to give that a new subscript, call it R23. And then I have resistor R4. Bring in R23. You might see this notation like R2 parallel R3, which is shorthand, so I don't have to write out this whole equation. R23 equals 1 over R2 plus 1 over R3. So I'm just going to write it as R23 for now, but remember I have this equation in the background for when I want to go plug everything in the end. Now I have 3 resistors in series. I can combine all of them in series to a single REQ, which is R1 plus R23 plus R4. And sorry, I forgot to label my voltage source here. Call that VS. and I have my current I through that circuit, right? So I now know I can solve for that current using Ohm's law. Vs equals I RAQ, and I can rearrange that for I equals Vs RAQ. So I know Vs, that's a given, and I know all the resistor values, so I can calculate RAQ, right? So now I know this current. That's a number I can calculate, okay? So now we've collapsed it. I can solve for the current. I'm now going to expand it back out. You can probably see where that's going. I know that in series, all those currents this current has to be the same as the current through each of these individual resistors. Then when I get back to that level, it's going to split between R2 and R3. Okay, so I'm going to try and fit all of this on one page here, kind of going over to this side. So splitting it back out, plus minus, there's R1, there's R23, there's R4, sure. And I didn't draw the ground symbol here, but say if I put a ground there, I'm going to define that as 0 volts. I know I have my voltage source up here, so that's Vs. Just to make life easier, in the meantime, I'm going to make up 2 more voltage variables. I'm going to call the voltage at that node or junction VA. I'm going to call that one VB. That's just to make my life easier with kind of writing down the math in between. And I know that VA, and if I look at my voltages going around the circuit here, VA is equal to the source voltage minus the drop over R1. So Vs minus V sub R1, which using Ohm's law is VA equals Vs minus I R1. So remember again, this current here, same as the current through each of these. So I already know I calculated that earlier. Now I know that I is the same through R1. So that means I now know VA. I know the voltage at that point, right? I can do the same thing for VB. It's kind of redundant to write it, but that VB is going to be 0 volts plus the voltage drop over R4. So I'm not going to have a negative voltage there, right? Again, this is where keeping track of the signs becomes important. Plus VR4, which, again, substituting Ohm's law in, is I times R4. And again, I know I from before, so now I know VB. Great, so now I know the voltages kind of at every point in the circuit. I expand it out one more time back to the original. There's R1, there's R2, there's R3, there's R4. So I expanded, but these 2 nodes are still VA and VB. Right, so the R23 here was just representing R2 and R3 in parallel, so I still know the voltages at those 2 nodes, right? So now, if I look at resistor R2, I just have a resistor and I know the voltage drop across it, right? So the voltage drop across R2 is VA minus VB. This is where that sign convention becomes important, right? If I had defined the signs for R2 the other way, then it would be VB minus VA. Okay, so ultimately, if I did that, when I went through, I would get a negative number for the current. So sorry, let me back up. It's kind of obvious which way current is flowing in this circuit, right? Kind of flowing clockwise. So when I finish this and solve for the current through R2, I'll get a positive number. I could have defined the signs the other way. That's fine. I just would have gotten a negative number for the current. Again, it's exactly like saying positive x is that way and then getting a negative number for your x velocity. I could have defined positive x the other way and gotten a positive number for my x velocity. Okay? So we still know VA and VB, and now you can just do Ohm's law and power and everything you would want for R2. So there's VR2, or I called it V2 up here, but that was one of the things we wanted initially. We know from Ohm's law that I2 is going to be that voltage VR2 over R2. So there we know the current. And then again, there's now 3 different ways you could calculate the power. P2, you could do I2, V2, or I2 squared R2, or V2 squared over R2. Great. Okay, so does that the process there again was to kind of collapse using equivalent resistors to the point that you just have a single Ohm's law circuit with just one battery and one resistor where you know the current, and then you can expand it back out, solving for voltages or currents as needed along the way. Okay? And this is kind of how I originally learned to do it in like high school physics before having taken linear algebra. So there may be more paths you could take to get to that point, but the point is kind of as you add more and more resistors, this becomes more of a pain in the butt to do. Okay, there's not necessarily a single, clear, systematic way to do it. So what we're going to talk about next is how you do this more systematically and use linear algebra to solve everything. But any questions on this process, which again, I think the problem maybe exactly like this or almost exactly like this was on homework 1, so clearly some of you like kind of figured out maybe you had a different method to do this, but question in the back.
On the image on the top right, why
yes.
did you draw a connection to ground?
Sorry?
Why did you draw a connection?
Why did I? But just because I was late, so do as I say, not as I do. I should have drawn that to begin with, just to define what 0 is. Again, if the ground symbol, 9 times out of 10 for circuits you see in this course, with a single battery, the negative terminal of the battery is going to be defined as ground. Again, think of it like, just like how I can choose how to assign the sign conventions for the resistors, I could decide to put ground up here if I wanted to, right? And that's just like referencing elevation relative to the ceiling instead of the floor. Like all my voltage, so that point would be 0, this point down here would be negative Vs, and so on. So I drew it there just because I realized that I had forgotten to mention that earlier, and I was too lazy to draw on every iteration of the diagram, just like I didn't redraw the signs each time. So again, going by the letter of the law, strictly speaking, like yeah, you should define that every time. If you ever see a circuit that's just a single battery with a negative terminal, your safest assumption is to assume that the negative terminal of the battery is defined as 0, because that's the most common convention. Okay. And again, so that's very much a like, not always practicing what I preach thing, so if you ever, feel free to call me out on that if you're like, hey, you didn't label your signs in that diagram, or you didn't tell us where ground is, or whatever. You can always ask me to clarify that. All right. Other questions on that process? Okay. Moving on to, I don't think we will have time to get through the full node analysis example today, but we are at least going to get started. Okay? Node analysis. Okay, so we are going to start by actually writing down the definition. I've probably been using the word node without defining it. What is a node? Junction of 2 or more elements or branches of a circuit. Again, my handwriting is terrible when I actually write stuff out, but node is a junction of 2 or more elements or branches of a circuit. So I'm going to draw something, and then we are going to do this one as a pole everywhere again. So we have a battery, Vs, 3 resistors, R1, R2, R3 in parallel. The question is, how many nodes does that circuit have? I'm going to put this one live as a multiple choice in a second, okay? That should be up. How many nodes does this circuit have? A single battery connected to 3 resistors in parallel. Okay. So far, you all agree that it is not 0, but there is significant disagreement over the correct answer. So, let's see, we're at about 100 responses. I think we got 120 last time, so I'll give it like another 20 or 30 seconds, and then we will switch over to show the results. Okay, so I'm going to leave this open for a second, switch over to the laptop. So far the majority, it is by far the majority answer is C. Everybody agrees it is not 0. But I'm going to ask you a follow-up question and leave that open so you can change your vote. Remember we talked, I can't remember if it was 1 or 2 lectures ago, about kind of equivalent ways of drawing circuit diagrams where things can be maybe geometrically different but electrically equivalent. Does it change your answer if I draw that circuit like this? R1, R2, R3. Poll is still open. Now first, would we all agree that the circuit on the left and the circuit on the right are electrically equivalent? Yeah. Does anyone disagree with that? Okay, so poll is still open. Does that change your answer? How many nodes does that circuit have? And feel free to talk to or argue with the person next to you about why they should or shouldn't change their vote. Like some people are sticking with their original answer, but most of you have shifted to 2, which is the correct answer. So I'm going to go ahead and deactivate this, but remember again, this was just participation, so if you clung to one of the incorrect answers, don't worry about it, although it's way more exciting when most people shift to the wrong answer, but it's kind of more boring when everybody goes with the right one. Okay. So this definition and kind of figuring out what's going on visually can be a little confusing at first, but it's important to understand going forward. So first, just because there is a dot drawn does not mean that counts as a node for circuit analysis purposes. And this is kind of an aside because you will see 2 different conventions depending on what textbook or data sheet you look at when wires cross. So one convention, say I have 3 wires like this. One convention is to draw a dot, meaning that those wires are electrically connected. So there is an electrical intersection at that point. So this is connected, and then they just do this to have the wires cross, right? So that means those wires are just kind of passing by and not touching each other. The other convention you might see is to use kind of a little loop to mean like, okay, if they intersect like that, they are connected, and if they don't, there's like the little bridge thing going over it. I prefer to kind of double up and make it super clear and do kind of the dot for a connection and the bridge for passing over, but again, this will vary depending on where you look. Website, textbook, even my own videos and resources, whatever. But point being, the dot does not always even mean, does not mean it counts as a node. Because if we look, for example, at these 2 dots that I drew, there's only this 0 resistance wire between them. They are not actually connecting 2 different elements in this circle, right? So the way the circuit is drawn here, this whole wire is really just a node that we just drew spread out to kind of make all the lines nice and perpendicular and parallel there, right? But that is electrically equivalent to just collapsing them all to a single point like that. Same thing on the bottom. This whole thing is the same as that. So this circuit only has 2 nodes. Okay, not if you guessed 8, maybe you were going by all the dots. If you thought 6, maybe you were like only counting the resistors, or 4, you were only counting these junctions and not that one or something. So going forward, that's the definition of node, right? If you can collapse the lines to just a single point, even if it makes the diagram messier, and that's how you wouldn't necessarily draw it, that's a node. Okay, not just all the dots or every single intersection of 2 lines. Okay, so is that definition clear? Okay. Let me double check. One more thing. So those are nodes. Nodes, and I'm going to write this down since I guess the poll everywhere. This circuit only has 2 nodes, not 4, 6, or 8. There is also a circuit definitions document on Canvas that has some more diagrams and the textbook definitions of this written out. So down in the resources section, if you want kind of the more textbook treatment, I have my own notes on it, and then it cites the page in the textbook that it came from if you really want to go look up like all the super literal textbook definitions. But this example is how I like to explain it, because I think that is more intuitive than just writing down the junction of 2 or more elements definition. Okay, we have 9 minutes left, so we are going to get started on the node analysis example after writing down one more thing. If you have a junction that is only between 2 elements, like this here, that is called a trivial node. Where again, it's just kind of connecting 2 things end to end, not 3 or more. And that definition, I think, becomes relevant for some node analysis problems. So, any question on the node thing, because we are now doing node analysis, so you need to know what a node is. Okay? Starting out node analysis, and again, we will get started here and then continue it on Monday. So I'm going to write down the steps that you use, and then you will need to, this is a very formulaic process, again, more systematic and kind of less chaotic than what we did before. So when you're doing this on a homework problem, you follow these exact same steps. Okay? It's very procedural. So step number 1, choose a reference node that is usually ground. Again, 9 times out of 10, it just kind of helps to define things relative to 0, which is going to be the negative terminal of the battery. You're going to define unknown variables for remaining nodes. So that's what I did kind of in the previous problem when I said, hey, to make this more convenient, I'm going to define VA and VB here. So that's your, you can use whatever subscripts you want. It could be VA, VB, V1, V2, whatever, except for the voltage source, because except for voltage sources, because that is known. So again, in the previous problem, we had VS for the voltage source. That's a given. You don't need to define that as an unknown variable. Then this is kind of the tricky part that's going to help us build the system of linear equations. We're going to apply KCL, that's Kirchhoff's current law. I'm not going to write that whole phrase out each time. At each node with a variable. This gives you equations with currents. For, I'm going to use Ohm's law to rewrite each equation in terms of voltages, which are the variables that you define as your unknowns. And then you're going to write a system of linear equations so, you have ax plus by plus cz equals d, or whatever you remember from linear algebra, right? If you get a bunch of equations in that form, you can then set it up as a system of matrix equations and just solve for all your unknowns all at once. So write system of linear equations and solve in matrix form. So, what do you think? We have 5 minutes left. I'm going to draw this problem out so we are set up to do it on Monday. So we're going to be using the same circuit we had before. We're just going to solve it differently. We have a voltage source Vs with resistors R1, oops, R2, R3, and R4. And I'm asking you to solve for I2, V2, and P2, so everything for resistor 2. But our goal is to get a system of equations in this form, AX equals B, where A is just a matrix full of constants that we know, X is our unknowns, and B is more constants. So if you remember your linear algebra, to solve for X, we can multiply both sides of this equation by A inverse, so we have X equals A inverse B. I'm not going to make you do linear algebra by hand in this class. You just punch that into MATLAB or your graphing calculator or whatever. Okay, so really quickly, just going through steps 1 and 2 of this process. Choosing our reference node, again, usually ground. So that's our reference node. Define unknown variables for remaining nodes except the voltage source, right? So we already know the voltage there has to be Vs. That's a given constant. If I look at remaining nodes in this circuit, so this is where that how many nodes are there question comes in. These are not nodes over here, right? I just have one node there and one node there. If I wanted to, I could redraw this with R3 like that, right? So if redrawing it like that makes it more clear that I only have 2 more nodes in this circuit that don't have defined voltages, and that's where I'm going to make up my variable names, VA and VB. Okay, so that is the setup for this process. The part about applying Kirchhoff's current law on each node takes more than the 3 minutes we have remaining, so I will save that for Monday. Okay? Have a good weekend. I'll be here for a few minutes if you have questions.